Farmer again. Welcome back to Software Engineering 2FA3, Discrete Mathematics and Applications 2. We're going to continue talking about Turing machines and computability, and today we're going to begin looking at recursive and recursively enumerable sets. So let A here be some set of strings over the alphabet sigma. And there's a proposition that's true. That's easy to see, easy to prove. If A is recursive, then the complement is also recursive. So if A is recursive, there is a Turing machine, some Turing machine M, that's total, that accepts A. And that Turing machine, we can modify it by switching the accept state with the reject state, and then that Turing machine will still be total, and it will then accept the complement of A. So it's pretty clear if A is recursive, then the complement will also be recursive. There's another proposition which also is easy to prove. If A and the complement are both RE, then A is recursive. This is because if we have a machine that accepts A and the machine that accepts the complement of A, we can build from these a machine that will simulate both of these. And if we give it an input X, this machine will check to see if X is accepted. And this machine will basically check to see if X is a member of A, and this machine will check to see if X is a member of the complement of A. So our machine will run both of these in parallel by running this one a few steps and running this one a few steps. And these machines, one or the other, will have to eventually accept, because X is either in A or it's in the complement of A. So if the first one accepts, then we accept X. And if the second one accepts, then we reject X. And so this machine will be total, and it will accept A. So yes, this proposition is true. If A and the complement of A are RE, then A must be recursive. Now, let's think about a decision problem, X being a member of a set A. So we have the set A. We want to know whether a particular given X is a member of A. So this problem can basically either be decidable, semi-decidable, or undecidable. Decidable means that A is recursive. That means there's a Turing machine that's total, and that Turing machine will allow us to know whether X is in A and whether X is not in A. A semi-decidable, it will be semi-decidable if A is RE. So if A is RE, there's some Turing machine that will accept A. And so if X is in A, we will know that. But if X is not in A, we will not necessarily know that, because our machine may not be total. And we'll say the problem is undecidable if A is non-recursive. If A is non-recursive, that means that there is not a Turing machine that will, when we run it on a given X, will either give us either accept or reject. Okay, so we can draw a little picture of what's going on here. We have here the RE sets, and here we have the recursive sets. And then the non-recursive sets, they're going to be all of these. Okay. There's another important theorem. This is a theorem we're going to call Theorem 1. If A is RE, then there's a Turing machine that will enumerate the members of A. So there's some Turing machine where this Turing machine won't take any input. Basically, it will start off with its tape like this, and it just has blanks. And when this Turing machine is allowed to run, what it will do is it will write down a string. And then it will put down a blank, and then it will write down another string. And it will keep doing this. It will print one string after another. And these strings will all be members of A. And if we wait long enough, every member of A will appear. So that's what it means for this Turing machine to enumerate the members of A. So if A is RE, remember RE means it's accepted by a Turing machine. If A is RE, then there is some other Turing machine that will enumerate the members of A. Okay, here's a question for you. Which of the following statements is true? These are all statements about being closed under complement. I'll give you a moment to think about this. Okay, welcome back. So A says that basically regular languages are closed under complement. We know that is true. B says deterministic context-free languages are closed under complement. We know that is also true. C says context-free languages are closed under complement. That is not true. D says that context-sensitive languages are closed under complement. That is true. E says that recursive languages are closed under complement. We know that that is true. And F says that RE languages are closed under complement. We know that is not true. Okay, let's move on. So far we've been using Turing machines to determine whether sets are recursively enumerable or recursive. We can also use them to determine whether functions are computable or not. And so let's say a Turing machine can compute an n-ary partial recursive function over the natural numbers as follows. The input alphabet will be 0 and 1, and the inputs and outputs of the function are going to be represented as binary strings. And the start state is going to be n binary strings separated by blank symbols that represent the n inputs to F. So if F has n inputs, we're going to start the tape like this. And we're going to have the first input, the second input, and so forth. So we have n inputs. And then M will be run, and if it halts with a new tape, new contents on the tape that looks like this, and this is a binary string of zeros and ones, this will be the output. So if these binary strings are the input, this will be the output. So if it halts in this form, that's the output. If it doesn't halt or halts with something in a different form, we'll say F is undefined in that input. So this allows us to think of Turing machines as being able to compute functions over the natural numbers. And so we have another theorem that says for all functions over the natural numbers, f is computable if and only if there is a Turing machine that computes it. So you can think of this as if we know there's some effective method for computing f, so it is computable, then there will be a Turing machine that will compute it. Okay, so let's sort of summarize how we can use Turing machines. We can use them to decide a decision problem. So this is going to be we're going to use a total Turing machine to do this. We can semi-decide a decision problem. When we semi-decide a decision problem, we can tell if X is a member of a set, but that's all. We can't tell if X is not a member of a set. So this is just using a Turing machine. We can compute a total function. We can do this with a total Turing machine. We can compute a partial function with the Turing machine. And then we can enumerate a set of values. This is another kind of Turing machine. Now, there are many equivalent definitions of a Turing machine. Some of them have two-way tapes. Some of them have multiple tapes. Some have a two-dimensional tape, so that's maybe a tape that looks like this, where the head can go this way, or it can go up and down. And we can have tapes where we have multiple heads, and Turing machines are non-deterministic. So there's many different kinds of Turing machines. And almost all of these are going to be equivalent. They're all going to, if one Turing machine will accept a language, then another Turing machine will accept the same language. So they're equivalent in that sense. Okay, we're going to end with a question. What is the distinguishing characteristic of a modern computer? Is it that modern computers can store and manipulate massive amounts of data with great speed and accuracy? Is it that they can access or control a large variety of peripheral devices? Is it that they can control and run programs? Or is it that they're implemented using electronic technology? What is the really distinguishing characteristic? So I'll let you think about that for a moment. Well, welcome back. This is really the distinguishing characteristic. What makes modern computers different than all computing devices of the past is they can store and run programs. So we're going to stop now. Well, let me just mention, we're going to stop here, but next time we're going to talk about undecidable decision problems. So see you then.